because RR, the route reflectors, can reflect iBGP updates between iBGP speakers. Hence, it doesn't apply iBGP split horizon rule, which protects the network against routing loops between iBGP speakers. Therefore, adding the route reflector can cause routing loops inside the autonomous system. Let's see now how adding the route reflector can cause routing loops. To remember iBGP split horizon rule, we can see this example. If we have R1 connected to R2 and there is eBGP peering session between them, R2 connected to R3 and there is iBGP session between them, R3 connected to R4 and there is iBGP session between them, and R5 connected to R4 and there is iBGP session between them, and finally R5 connected to R2 and there is iBGP session between them. If there is eBGP update sent from R1 to R2, R2 can resend this BGP update to R3, R3 to R4, R4 to R5, and R5 to R2. If for some reason R1 stopped sending this eBGP update to R2, R2 would accept the iBGP update coming from R5 about the original network. Therefore, iBGP routing loop would occur between R2, R3, R4, and R5. To recover this issue, split horizon rule must be applied. Split horizon rule says that if a router like R3 received iBGP update, it cannot resend this iBGP update to another iBGP peer. R3 cannot send the iBGP update to R4. Therefore, the routing loops would be prevented here. But what if we replaced R3 by a route reflector, RR3, and we replaced R4 by another route reflector, RR4? The BGP update will be sent from R2 to route reflector 3, and route reflector 3 would be able to send and reflect this route to RR4 or route reflector 4, and route reflector 4 can send this iBGP update to R5. R5 would not be able to resend this BGP update to R2 because it's a normal iBGP session between R5 and R2, and iBGP split horizon rule is applied here. But RR4 has iBGP peering session with R2. It can send the received BGP update from RR3 to R2 because RR4 has R2 as a client. It can send the coming normal iBGP update to a client peer, and if for some reason again the eBGP update stopped sending from R1 to R2, R2 would be able to accept the coming iBGP update from RR4. Therefore, iBGP routing loop would occur again between R2, RR3, RR4, and R2. We can see another example. If we have R1 and R2 and there are two route reflectors, RR1 and RR2, and each route reflector has R1 and R2 as client. RR1 has R1 and R2 as iBGP clients, RR2 has R1 and R2 as iBGP clients. And we have another routers, R3 and R4, and they peer with another two route reflectors. If we have a large network and a large number of routers, we can divide this large number of routers into clusters, and each cluster has its own route reflectors. We add in each clusters two route reflectors for more resiliency. Therefore, we have R3 and R4 in another cluster with another two route reflectors, RR3 and RR4, and the route reflectors in the different clusters peer with each other. If a BGP update sent from R1 to RR1, RR1 would reflect the received iBGP update to R2 and can reflect this BGP update to RR3, and RR3 can reflect this BGP update to RR4, RR4 can reflect this BGP update to RR2, and RR2 can reflect again the original BGP update to RR1. If for some reason the BGP update is not coming from R1, RR1 would be able to accept the original BGP update that was coming from R1 from RR2. Therefore, iBGP routing loops would occur again here. Therefore, deploying RR in the network can cause routing loops, especially if we have a multiple of route reflectors in the network for more resiliency. But adding a multiple of route reflectors can cause routing loops with the iBGP peers, iBGP clients, or with the different route reflectors in different clusters. To recover the routing loops issue with the route reflector, two special BGP attributes added for RR, for the route reflector, as line of defense against routing loops. The first line of defense is originator ID. The second line of defense is cluster list. Back again to the example where we discussed the issue of having iBGP routing loops between R2 and RR3 and RR4. Now we can discuss adding the originator ID attribute. When R2 sends iBGP update to RR3 and RR3 is going to reflect the received iBGP route from R2, RR3 as a route reflector will add the originator ID. The originator ID here would be the router ID of R2. Therefore, the originator ID attribute will be added from the first route reflector, which is RR3, to any other iBGP peer. RR3 has iBGP peer with RR4 and it can send the iBGP update normally to RR4. RR4 as a second route reflector would not change the originator ID, which is RR2. Therefore, when RR4 reflects again the iBGP update coming originally from R2, it will send this iBGP update included with the originator ID as R2 ID. When the iBGP update arrives to R2 and R2 checks the originator ID and finds out that the originator ID is R2 ID, which is the ID of R2 itself, it would discard the iBGP update coming from RR4, and that would prevent iBGP routing loops to occur between R2, RR3 and RR4 using the originator ID attribute. Back to the example where we discussed the issue of having routing loops between different route reflectors in different clusters. We have two clusters here. The first cluster includes RR1 and RR2 with their clients R1 and R2, and the second cluster includes RR3 and RR4 and includes R3 and R4. And now we have to discuss the importance of having cluster ID attribute that will be added to the iBGP update sent from any route reflector. Now, when RR1 receives iBGP update from R1, RR1 will reflect this iBGP update with adding its cluster ID to the cluster list attribute in the iBGP update to RR3. And RR3, when it reflects this iBGP update to RR4, it adds its cluster ID to the iBGP update to RR4. Now the cluster list would be RR1 and RR3, and RR4 would do same, will add its cluster ID to the cluster list before sending this iBGP update to RR2. The cluster list would be RR1, RR3, RR4, and same, when RR2 reflects this iBGP update back to RR1, it includes its cluster ID in the cluster list attribute. Now the cluster list is RR1, RR3, RR4, and RR2. When RR1 receives iBGP update, it would check the cluster list attribute. RR1 would see its cluster ID in the cluster list, means that this IBGP update sent from itself, and it would discard IBGP update that would protect the route reflectors from having IBGP routing loops among each other.